Hello. In this video, we're going to talk about the case number 2 in oblique triangles, which is sometimes referred to as the ambiguous case, because sometimes when provided three measurements within a non-right triangle, those measurements might not create an actual triangle. They may end up creating two different and unique triangles, and they may produce exactly one triangle that fits the criteria. And I'd like to talk about those scenarios in this video. So here's a diagram, and hopefully you can see it on your screen. This website's not really responding well while I'm trying to record it, but it's meant to visualize, or meant to help you visualize, the ambiguous case of the law of sines. I'm going to extend the length of one of these sides by using this slider here. So hopefully you can see that the side length on this side of the triangle has extended. And also I hope you recognize too that two side lengths of this um, triangle are provided while an angle measure not in between them is also provided. So this diagram, while it's not a triangle right now, does represent a side-side angle situation, and we hope that it will create a triangle. Now, if I extend that side length and I reduce this side length here, side length B, because only angle measure down here, down in the left-hand corner, the non-included angle measure is specified, this angle measure has to be held in place. That allows this side over here to swing freely. And so we sometimes call this the swinging leg or swinging gate of the case number 2. You'll notice that no angle measure that I select, there's no position where this can swing to that retains the side length for this side of the triangle and the side length of this side of the triangle. No position that I slide this final corner to will actually create a triangle. Now, even though I've specified side length 1 and side length 2 and an excluded angle measure, there's no way for me to create that triangle. And so this would be a situation akin to this first example here, where there is no solution. Now, when we're talking about A, H, and B, what we're trying to emphasize here is that, say, side length A is provided, side length B is provided, and an implied angle measure is provided. But the height from the implied base of this triangle, the height has to be measured perpendicular to that base. If I were to measure the height from that base to the peak here, if that height is less than side length A, sorry, I read that backwards, greater than side length A and less than side length B, which isn't quite appropriate for this diagram, but hopefully you can understand that here, that if side length H is in between the lengths of A and B, then the triangle cannot be completed, and there is no such a diagram that fits the provided information. Now, similarly, two solutions, two unique triangles can be created if the appropriate scenario has been generated. And that happens when when the height of the triangle along its base is less than both A and B. Let me try to share that example here. If this side length is fixed and this side length is fixed while this angle measure in the bottom left-hand corner is also fixed, you'll notice that when I slide this position down to that point, here we've created a triangle with side length that's specified on the right side and left side. With the angle measure not included between those two, we have a triangle here. And this triangle side length is some value. It's actually quite similar to the two that are provided already. But if I had swung this triangle further, say to here, we still meet the criteria where this side length on the right and left are provided, along with the angle measure not included in between, yet the third side length of this triangle is much smaller than before. And therefore, we've created a second triangle that meets the same criteria that were given. So again, here's one triangle that meets the criteria that are supplied of the side-side angle triangle. And here's another one that meets that criteria as well. And in the third scenario, if side length A and the height of the triangle are the same, and both of those are less than side length B, then essentially what we're doing is we're creating a right triangle. And there's only a single right triangle that meets those criteria of the provided information. So that's a little hard to replicate in this diagram, but if the height of the triangle is the same as the side length associated over here, well, if the side length and the height are the same, well, the angle measure in this corner has to be 90 degrees, and we're dealing with a right triangle. So the time that case number 2 produces exactly one solution, we will find ourselves working with a right triangle. So let's try solving this particular triangle. Now again, a diagram is not provided, so we don't know exactly what this thing's going to look like, but we should be able to solve it for all side lengths and angle measures. So let's go ahead and build a table here of our information. We've got angle measure A, which is 36 degrees, angle measure B, and angle measure C we're looking for. We've got side length that's of A that's equal to 5, side length of B that's equal to 8, and side length C that's unknown. So when we're all done, we should have a solution for all 6 of these components. Now, what's that going to look like? Let's see if we can sketch a fairly accurate diagram here. This doesn't have to be perfect, but it should be pretty close to being correct. I'm going to sketch this triangle this way and place angle measure A in the bottom left-hand corner. That's 36 degrees. That means angle measure B is here and angle measure C is here. Side length A is equal to 5 units, and you'll notice its length is rather short, whereas side length B across from angle measure B is equal to 8. Now, in this particular instance, you'll notice that side length A, the length across this diagonal, is going to be longer than the height of the triangle. And similarly, side length B is also longer than the height of the triangle. And since since A and B are both greater than side length H, the height of the triangle, then we should recognize that there are two solutions possible. In fact, you might be able to see it yourself, and you could have imagined it on your own already. What if I label side length B this direction, side length A in this direction, then side length C in this direction? We still have a 36-degree angle in the bottom left-hand corner. We still have a side length of B equals 8 across this diagonal. We still have a side length A across this diagonal of 5 degrees, but angle B is now an obtuse angle, whereas up here it appeared to be acute. So angle B, angle C, as well as side length C are going to be different in this particular example. But here again, they will satisfy the provided information. So let's go ahead and solve this. Even though this is labeled the ambiguous case, we still use the law of sines to solve it. And the law of sines states that sine of angle A divided by side length A is equivalent to sine of B divided by B, which is also equivalent to sine of C divided by side length C. Now, I think I'm going to ignore this component of the law for just a moment because I'll note that sine of A, well, A is provided, divided by side length A, that produces a ratio for me to use. And we know that sine of angle B, which is unknown, is going to be divided by side length 8. Now, it's angle measure B that I'm going after here, so I'll probably need 2 steps to do so. I do recognize that the cross products are equal, and when I multiply across this diagonal, I can divide by the third numerical value, and that's going to give me this result. The issue that we're facing here, though, is that this result is not b by itself, but sine evaluated at b. So what we're saying is that sine of b, that expression, is equal to 8 times sine of 36 degrees divided by 5. And as you recall from prior lessons and prior videos, we can isolate the value b by applying the inverse of sine to both sides of the equation. And if I apply sine inverse to the right-hand side specifically, we will obtain the value for b. And if I evaluate this expression, as I've done off camera here with my calculator, I see that angle measure b is equal to 70.1283 degrees. So it looks like angle measure b is 70.1283 degrees. And if I subtract these two angles from 180 degrees, that means that that angle measure C is equal to 73.8717. The sum of these three angle measures is now 180 degrees. And lastly, we can solve for side length C, again using the proportions of the law of sines. And so the law of sines would look something like this. Sine of angle A divided by side length A is equal to sine of angle C divided by side length C. And using cross multiplication and division, we should be able to, going the wrong direction there. If I use cross multiplication, multiply these two values across the diagonal, divide by the third value in the group of 4, that should generate the result for this component down here, which will be C by itself. So sine of 73.8716 degrees times 5 divided by sine of 36 degrees gives me side length C, which appears to be 8.1717 units in length. 8.1717. So the results in this box do seem to correlate with the diagram that was shown over here. Side length C is 8.1717. That's clearly longer than side length B, and that's what this diagram represents. Angle measure B is approximately 70.1 degrees, and then angle measure C is 73.87 or 73.9. This diagram's not perfect. The way it was sketched, it kind of looks like angle C should have been obtuse, but the calculated result was just 73 degrees and not greater than 90. But that's okay. Again, the diagram was just used for us to establish appropriate methods for solving this triangle. So you might be asking yourself, well, how do I find the other triangle if the calculator has spit out results and given me these three values? Won't it just produce the same results for the next triangle? And the answer is yes, but what we should be aware of is the following. In this scenario, when there are two solutions available, the calculator result of 70.1 degrees for angle B, that was the first angle measure that we calculated, that angle measure is also equivalent to the other form of the triangle, where its angle measure here on the outside is 70.1, in this case 283 degrees. And so therefore, the angle measure B in the alternate case is actually the supplement to the result that the calculator provided. 180 degrees minus 70.1283 would also work for angle B. So therefore, angle B might actually be 109.8717. And if angle B is 109.8717, and angle A is still 36 degrees, then angle C is going to be 34.1283. 1283 degrees. And now this diagram is starting to look more and more like the angle measures that we've just computed here. Certainly this side length could be 109 degrees, 109.9, and then therefore this angle measure could be 34.1 degrees. Okay, and then that means side length C is going to have to be a whole lot shorter than the 8.17 that we saw just a minute ago. And we'll see that if we set up the law of sines again. Sine of 36 degrees divided by the side length that's across from it, in this case 5, will be equal to sine of 34.1283 degrees divided by side length C across from it. So this side length is across from side length, this angle measure is across from side length C. And we can cross multiply to solve for C. So we'll multiply across this diagonal, divide by this result, and we'll end up with side length C. So here's the setup, and if I use the calculator off screen to solve, I see a result of 4.7726 units. So it looks like side length C in this case is 4.7726. And that is indeed different than the initial triangle that we solved. So when you're dealing with this situation, this particular case, it presents itself when you're solving a triangle that falls under case number 2. And let me just make a note down here. There is ambiguity when, first off, you're dealing with the SSA case, which is case number 2, and there's no diagram provided. If the diagram's provided, most of the time we can assume that it's drawn to scale and fairly accurately. In this case, there was no diagram, so we weren't sure which solution would be appropriate. But we would be able to determine when there's two solutions, one solution or no solution, by solving for side length or height h of the oblique triangle. And perhaps you've noticed that this triangle here inside of our oblique triangle is a right triangle. And you can use the trigonometric function sine to solve for h. And that would be true in all of these cases. So if sine of 36 degrees is equal to the opposite side length divided by the hypotenuse using simple right triangle trigonometry, you'll notice that side length h in this case is 4.7023 units in length, and that 4.7 is less than both 5 and 8. Since h 4.7 was less than both 5 and 8, then we would have recognized that there are two solutions to that triangle. I would like for you to solve this final triangle on your own by first considering the generic shape of the triangle. So let's just draw a generic shape here, and we could label this again A, B, C. We've got angle measure A, which is 40 degrees, side length A, which is across from that at 7 units in length, and side length B, which is across from this angle measure of 10 units in length. So clearly we're dealing with an SSA triangle, which is case number 2. and there's no diagram given, so there is some ambiguity here. In this example, it's this side length that becomes the swinging leg because this angle measure is fixed, and with this short side 7, well, it could be here, but perhaps it could be here as well, and we'd have two different triangles. And so what I'd like to do is determine the height of the triangle in this perspective. So what if we had the height measured from angle C straight down to this side length? Here's our 90-degree angle. Side length H right here, the height of the triangle, is pretty easy to compute. And again, if it's not clear, I'm creating a right triangle here whose opposite side length is H, and the hypotenuse length is 10. So sine of 40 degrees is equal to H divided by 10. H is equal to 10 times sine of 40 degrees, which is 6.4287. And 6.4287 for H is less than side length A. It's also less than side length B. So therefore, there will be two solutions to this triangle. So take a few minutes and try to solve for both of them on your own. And I will ask that you pause the video now and resume playback in a moment to check your work. So here's the work that I showed to complete this particular example. Again, we're reminded that H is equal to 6.4, which is less than both side length A and B. I took the time here to redraw the diagram a little bit more carefully and oriented it in such a way that the height is measured vertically. So again, hopefully you can see that this swinging leg, side length A here, when positioned in this position, will give us an angle measure of 66 degrees for angle B. But if it's swung to the left, angle B is 113.3, because again, that complement 113.3, I'm sorry, not complement, but supplement is 66.7. The sum of these two is 180 degrees. Now, if you're still having trouble seeing the solutions to these or the approach to this particular set of problems, please do search for the ambiguous case number 2 on YouTube, or search for the phrase law of sines ambiguous case. And certainly you'll find other videos that do a fine job of explaining this situation. And as always, you can bring questions to class or send them to me through email or Schoology, and I'll do my best to answer and address them then. Thanks for watching.